since I'm out of town, I'm going to basically be working on a pad of paper here and talking you through some of the lecture. We've been dealing with DFTs, and I want to start talking or get down to actually writing down some DFT properties. And so we've been dealing with properties all the time here, and it's kind of good to get them all down in one place. So for these properties, they're mostly things we've seen before. I want to just write them down and talk about them a little bit. So most of them we get kind of for free. We've already done them. We've already mentioned that the DFT is going to be a periodic function. After all, the way we got the DFT was we sampled the DTFT, and that was periodic with period 1. Well, when we take a DFT, we're sampling and we get a total of n samples. So the periodicity here for the DFT is that we have a period of n samples. And what we said was that my time domain signal, x of n, is also periodic once I've sampled in the frequency domain. We're dealing really with that periodic extension of the original waveform. And so this is true for all n, right? And so my time domain waveform ends up being periodic, and that's the signal that I'm always going to be processing if I'm dealing with an FFT or a DFT or one of these numerical algorithms that deals with samples in the frequency domain. I also get a periodic function in the frequency domain. Now I've sampled, so if I offset that sample by n values, I end up with just the same value again. And again, this is the DTFT being periodic with period 1. So this is true for all k as well. Okay, so when we do a manipulation, either time or frequency, we're always going to deal with a periodic function. Okay, we'd mentioned linearity. We've been using linearity all along. If I have a linear combination of input signals, my DFT is just the linear combination of the individual DFTs. We have some symmetry properties. And there are lots of these, and we mentioned a few of them for the DTFT. They're basically the same properties that we've had before, but and one of the ones we had before for the DTFT is we had a conjugate symmetry property. So x of n real implied that if I looked at x of minus f, that was the same as x of f, but it always had to be the complex conjugate of that, right? Okay, so we had this property already for the DTFT. For the DFT, I'm going to sample this, but again, remember when I collect my samples, I'm really only going to sample for f between 0 and a little less than 1, right? I collect n samples. So this is going to be n samples over that range to come up with what we call the DFT as opposed to the DTFT. So here's my DTFT property. The DFT property, I'm going to talk about the symmetry in this collection of samples. And it's exactly the same property, except I don't usually talk about negative indexes on my DFT, right? And so instead of talking about a negative index, I'm going to offset that by a value of 1 to get to the positive index. And so my symmetry property ends up just being that if x of n is real, that means that when I look at any given sample in the DFT, that's going to end up being a conjugate of another sample someplace else in that array. And the way I locate that is I look at n minus k. So instead of talking about negative k values, I offset it by my n samples. My DFT is always periodic with a period of n, and I end up with the same property. Okay. My next property, 4, deals with multiplication or and if anytime we're talking about multiplication of signals, I'm going to also talk about convolution, right? Okay, so multiplication and convolution, we have this kind of duality between the transforms in the time domain and convolving in the frequency domain. So here's why I end up using a DFT often, right? I have this nice efficient algorithm for calculating frequency domain values. I'd love to be able to multiply their transforms together instead of doing a convolution. There's my alternative, right? And so this one is a little bit tricky because of all the periodic extensions. Everything we're dealing with is periodic. So what we're going to assume is that I have x1 of n, and it has a transform pair x1 of k, and x2 of n, and we can calculate its DFT and get x2 of k, a whole set of samples in the frequency domain for each of these time domain blocks of samples. So there's a block algorithm. And I'm going to assume that I have an n sample DFT for each so that the frequency domain samples correspond to each other. And then I'm going to define x3 of n to be the inverse DFT of what I get when I multiply these two together, x1 of k multiplied by x2 of k. Okay? So I don't know, calculate the two transforms, multiply in the frequency domain, find the inverse transform. And what I'd love to see is this thing ending up being just the convolution of these two. And that means that I'm valid using a DFT to calculate convolution of two functions in the frequency domain. I have these fast algorithms for DFT and I'd love to use them this way. So there's what I'm after. And then to get to that result, I actually got to do a fair amount of work, right? And so I'm going to actually write down here what x3 of n is. And it's an inverse transform, so I have this 1 over n factor, and then I have a summation k going 0 to n minus 1 of two different transforms multiplied together. So to write x1 of k, I'm going to take another sum, m going 0 to n minus 1, x1 of m, times e to the j 2 pi m k over n. There's x1 of m, right? And then I got to multiply that. This is going to be a long expression. I got to multiply that by exactly the same thing. So this is times. I got to multiply that by another sum over. Oh, now I'm sure I'm getting off of the screen here. So let me move up a little bit. Another sum. I'm going to take a sum over values of L for a different index, x2 of L times exponential with an L factor up there. And all of this stuff from here to here has got to be multiplied by well, I got to find an inverse transform. I'm summing over values of k and I want a value of n out. So I got to multiply that by e to the, gosh, these should be negatives up here. Negatives, right? And this is going to be for the inverse transform, e to the plus j 2 pi times n times L over n. Okay? Oh man. So here's a nasty expression here. I've got a total of three sums. I have a sum over values of k, I have a sum over values of m, a sum over values of L, and they're all multiplied together. Now, what I'm going to do is multiply all of this out, okay? And I get terms in here that depend on m and L that are going to depend on the input sequence values, right? And I also get an exponential term that's added up, right? And so if I multiply that out and I change the order of the summation, I end up with x3 of n being this 1 over n, sorry. And I have a summation, and I have a summation over every single value. But I'm going to choose the sum over values of m and L first. And these go all the sums go from 0 to n minus 1. Right? And I'll have x1 of n, m. I have an x2 of L, right? And then all of that, see, I need one more summation, so I have a sum over k. But since these factors don't depend on k, I can go ahead and work that sum out ahead of time. So that's times a summation over values of k of, this is k going from 0 to n minus 1. Sum over values of k, and it's this exponential term I have in here. So this is going to be e to the, gosh, what do I have? I have j, e to the minus j 2 pi. Okay, what do I got? I have a minus m. There's a minus sign already there. So I get an m minus l, and then plus k. No, not k, n, right? Oh, now I'm going to have to think about this here. Okay. I have an m, an l, and an n factor out. Okay. All right. Now, okay. So here's the part of the sum that I'm actually able to work ahead of time, right? Because it doesn't depend on the value of m. Now, I'm going to take a break right now, and we'll come right back to this spot on the next lecture just to keep things under 15-minute segments. So we'll pick it up right here.